if you look at the textbook or any textbook, they summarize many other indeterminate forms. But I really do not want you to memorize too many forms. Okay, you just remember the L'Hopital's rule can only be applied to an indeterminate quotient. For any other form, you need to convert the limit to a limit of a quotient. Okay. Questions. So number 6 is designed for that purpose. Okay. You don't see a quotient, right? So the first thing you do is to convert the limit to the limit of a quotient. In particular, you want to convert the limit to an indeterminate quotient. Okay. Okay. Now, how to do the conversion? And so basically, the idea is to rewrite the limit to the limit of a quotient. Okay, first. In some cases, there's more than one way to convert the limit to a quotient. So maybe some ways will not work, but some way will work. You don't have to get the thing right at the first time. You can try. Okay. Now let's try something first. Okay. Now the limit as x approaches infinity. Okay. We want to convert the limit to the limit of a quotient. Okay. We take out a common factor first. Okay. We take out a common factor of x first, right? And then e to the power of 1 over x minus 1. All of you guys know what's going on here. Okay. Okay, now a quotient. We want to convert the thing to a quotient. How do we convert the thing to a quotient? As the limit as x goes to infinity. I will try to ask you some question, okay? If I leave the stuff, the function in the brackets on the numerator, what would be the denominator if we convert the function to a quotient? So just tell me what should be the denominator here. Here you have x.
1 by x.
Yeah, 1 by x, 1 over x is the same thing. Okay. If you have trouble with this, you could be in trouble. You just try to divide the two fractions. You're going to return this to this. Okay. I think all of you guys know what's going on here. So just a little conversion. Okay. Okay. Again, for that function, there might be two ways to convert the function to a quotient, but one way will work. Actually, that way will work. Okay. Now, the next step, we are going to verify the condition. We are going to verify the limit of this quotient is indeed an indeterminate quotient. Later on, I'm going to tell you why we call it an indeterminate quotient. What we mean by indeterminate. Okay. Actually, for indeterminate quotient, the answer can be a finite number, can be infinity, can also not exist, can also be 0. Okay, that's why we call it indeterminate. Okay. So very shortly, I'm going to make more comments. But now we'll move on to verify this limit is indeed an indeterminate quotient. I'm going to use my notation. Okay, again, it's only my convention. Okay, as x approaches infinity, what is the limit of the denominator? As x goes to infinity, what is the limit of 1 over x? As x gets larger and larger positive, 1 over x approaches 0, right? So 0 is the limit of the denominator. Okay. You just imagine as x gets larger and larger positive, x gets tinier and tinier. Okay. The next thing you have to verify honestly, as x gets larger and larger positive, what is the limit of the numerator? As x approaches infinity, what's the limit of the numerator? Now follow me, okay? as x approaches infinity, as x gets larger and larger positive, 1 over x gets closer and closer to 0, tinier and tinier. By tiny I mean very close to 0. Okay. And then e to the power of x gets closer and closer to 1 because e to the power of 0 is equal to 1. So that makes sense? And then 1 minus 1 is equal to 0. I'm trying to say as x gets larger and larger positive, e to the power of 1 over x minus 1 gets closer and closer to 0, which means the limit of the numerator is equal to 0. You use a notation like that to indicate the limit of the numerator is equal to 0. Again, that's only my conversion. Okay. I mean the notation. Okay. If you do it anywhere else, you need to verify the conditions by writing some words. Okay. So we are ready to apply the L'Hopital's rule. Okay. The condition is satisfied. Now we are going to apply the L'Hopital's rule. Okay. The limit as x approaches infinity, and then we differentiate the numerator and the denominator. Okay. I told you to memorize the derivative of the denominator of 1 over x before. I told you to memorize because we are using it over and over again. The derivative of the denominator 1 over x is negative 1 over x squared. I told you to memorize before, right? And then the derivative of the numerator, because it's the first Math 102 class, I need to review something from Math 101. The derivative of the numerator, you need to differentiate e to the power of 1 over x, right? You see chain rule in here again. You have to use the chain rule. Okay. You choose 1 over x as u. You differentiate e to the power of u first. E to the power of u. E to the power of u is e to the power of u. E to the power of 1 over x. I said u, I wrote 1 over x, followed by the derivative of u, because we are using chain rule, right? The derivative of u is negative 1 over x squared. I'm 100% sure this derivative is one of the questions we did in Math 101. I told you that's, in most cases, my first question to ask you to do in Math 102, but I forgot to ask you to do that. And this time. Okay, taking the derivative of the numerator, we have e to the power of 1 over x, and then times, I'm copying from here, don't look at my cursor, okay, and then times negative 1 over x squared. Simplify. Now simplify. Okay. Why can we cancel out that factor? As x approaches infinity, this factor is a non-zero number, right? Approaches infinity, it means x gets larger and larger. In any case, that factor is a non-zero number. That factor is not equal to 0, I mean. Okay. That's why we can cancel out a non-zero factor. So I think I have enough room to finish this. So we end up with the limit as x approaches infinity, the limit of that. The function is e to the power of 1 over x. We end up with that limit. Okay. For this one, we do not have to use any L'Hopital's rule or whatever rule again. Anybody want to tell me the limit? The limit of this? I mentioned earlier. Okay. As x gets larger and larger positive, 1 over x gets tinier and tinier, gets closer and closer to 0. And the e to the power of something getting closer and closer to 0 is e to the power of 0, right? E to the power of 0
is 1.
Is 1. Okay.